Okay, so this now will be, you see, the square root of that. The square root will give me, that is 53,850.16 meters per second. Okay, 850.16 meters per second. That is it. Okay, and remember this was what we solved for what's it called, the planet A. We had the weight of planet A as 157.6. So we had the weight of planet A as 157.6 Newton. Okay, and then the escape velocity as 53,850.16. That is 53,850.16 meters per second. Okay, so let's solve for planet B. For planet B, the mass MP is equal to a question mark. Mass MP equal to a question mark. That is, the mass is unknown. That is it. Planet B, the mass is unknown. The mass of planet B is unknown. And then the diameter was given to us as 1.28 times 10 raised to the power 7 meter. 1.28 times 10 raised to the power 7 meter. So we take that. Take the diameter. Diameter was given as, diameter D is 1.28 times 10 raised to the power 7 meter. Okay. Then you find the radius. The radius now, radius of the planet arrow is half of the diameter, which is 1.28 times 10 raised to the power 7 divided by 2. So arrow will be equals to, I find that half of 1.28 will give us, okay, if you divide that, you'll be having 6,400,000 in meters. Okay, that is 6,400,000, which is equals to 6.4 times 10 raised to the power 6 meters. Okay, standard form, 1 2 3 4 5 6, 1 2 3 4 5 6. Okay, that is it. The decimal point comes here. That will be 6.4 times 10 raised to the power 6 meters in standard form. So the radius of that planet is that. Now let's look at how we can find, okay, the weight was given to us as 98 Newton. The weight of the 10 kg ball in that case, so the weight of 10 kg ball was given to us as 98 Newton. Okay, and also we remember that W is equals to mg, so you can make M the subject of formula. G, you can make G the subject of formula there. So you say that G will be equals to W over M, right? And the weight is 98. 98 divided by the mass is 10 kg. The mass is 10 kg. That is it. The mass is 10 kg. Okay, so 98 divided by 10 will give me 9.8 meters per second square. Okay, 9.8 meters per second square. So it means that G is 9.8 meters per second square. That's acceleration due to gravity. Okay, now since you have gotten this, now we can then look for the value of MP, that's the mass of the planet. We know that G is capital G M over R square, isn't it? So we can make the mass MP subject of formula. So the mass of the planet now, we have G. If I cross multiply, I have that G MP will be equals to G R square. So that MP, mass of the planet, will be G R square divided by capital G. Okay, so the mass of the planet is G R square over the gravitational constant. So if I substitute into that formula now, I'll be having something like this. By means of substitution, I'll be having that MP in place of small g, I write 9.8, okay, times, that is this, 9.8 times the radius there is 6.4 times 10 raised to power 6 as all raised to power 2 all over gravitational constant is 6.67 times 10 raised to power minus 11. Okay, so if I multiply now, I have that the mass of the planet MP will be 9.8 times, if I square that, I'll be having 4.096 times 10 raised to power 13 divided by 6.67 times 10 raised to power minus 11. Okay, so I multiply the numerator and I'll have, so when I multiply this, that will give me, this is 4.01408 times 10, that's 4.01408 times 10 raised to power 14 divided by 6.67 times 10 raised to power minus 11. Okay, so if I now do the division, if I divide this now, I'll be having, okay, if I divide this will give me 6.018 times 10 raised to power 24 kilogram. Okay, 6.018 times 10 raised to power 24 kilogram. Okay, so if you look at this, actually you find out that this planet, we have obtained the mass of the planet as 6.018 times 10 raised to power 24 kilogram. And then we also obtained its escape velocity. Okay, escape velocity has not been solved. We'll solve that. Let's get the escape velocity. The escape velocity there, let's work it out. Escape velocity VE is the square root of 2gr, which is VE is square root of 2 times g is 9.8, that is g here is 9.8 meters per second square, times, and r is 6.4 times 10 raised to power 6, that's 6.4 times 10 raised to power 6. So I'll be having VE as the square root of, so this will give me 125,440,000. Okay, that's when I multiply that, and then I'll find the square root. It gives me, my escape velocity is 11,200 meters per second, or 1.12 times 10 raised to power 4 meters per second. That's 1, 2, go 1, 2, 3, 4. Okay, so that is it. So 1.12 times 10 raised to power 4 meters per second is standard form. Okay, so what are your observations? First, you write that down. This is 1.12 times 10 raised to power 4 meters per second. Okay, you observe that the planet B is the Earth. Reason being that the radius of the Earth is 6.4 times 10 raised to power 6 meters, and the acceleration due to gravity on the Earth's surface is 9.8 meters per second square, which is approximately 10 meters per second square to the nearest whole number. So once you see this, just know the acceleration due to gravity is 9.8 meters per second square. That is that of the Earth. Acceleration due to gravity on the Earth's surface, GE. Acceleration due to gravity on the Earth's surface is 9.8 meters per second square. Okay, take note. It is approximately 10 meters per second square. So this is it. Okay, so that is it. Take note. And the radius of the Earth is 6.4 times 10 raised to power 6. So this planet B is the Earth. Now let's solve for that of planet C. Let's solve for planet C. Okay, so for planet C, first we take the mass. The mass of the planet is 7.4 times 10 raised to power 22 kilogram. That is 7.4 times 10 raised to power 22 kg. That is the mass of planet C. Then the diameter was not given to us. We take the diameter. The diameter was not given. The diameter D was not given. So we write that down, question mark. Then we are also given the weight of 10 kg ball as 16 Newton. Weight of 10 kg ball. See, weight of 10 kg ball was given to us as 16 Newton. the weight of 10 kg ball was given as 16 Newton. Alright, and then we know that weight W is equals to mg, isn't it? So we can then make G the subject of formula. That's G will be W over m. Okay, that is it. We know that G is force per unit mass. Okay, so which is similar to this, right? So this now, knowing that the mass of that ball is 10 kg, right? The mass of the ball is 10 kg. That is this. It's 10 kg. So I'll place it into the formula, and acceleration due to gravity now will be, the weight is 16 Newton. 16 divided by 10, that is 1.6 meters per second square. That's my acceleration due to gravity in this case. So acceleration due to gravity is 1.6 meters per second square. Now we also come back to the formula that acceleration due to gravity is Gm over r square. Okay, so we should know that acceleration to the gravity is this. That's the gravitational field intensity, is the gravitational constant times the mass of a planet over r. So we call this mp, mass of the planet. Alright, so the next thing we'll do now, we are going to make this what's it called, the mass of the planet. The mass of the planet is given to us. Make r subject of formula. So if I cross multiply, I'll have g r square equals to gmp. Okay, so it means that r square will be equals to gmp divided by small g. So if I take the square root now, both sides, taking the square root, I'm having that r square times half, so eliminate, equals to gmp over g all raised to the power of half. Okay, and so I will get that r is equals to gmp over g square root. Okay, that is the radius of that planet is given by this formula. So we can then solve, and we'll be having a substitution. Having r as this square root of, so I'm having that r now, the radius of the planet r is equals to square root of, my gravitational constant is 6.67 times 10 raised to the power minus 11, and the mass of the planet was given to us as 7.4 exponent 22. That is 7.4 exponent 22 all over. Then we obtained acceleration to gravity on that planet as 1.6. Okay, we obtained it as 1.6. So it means that the radius of the planet now will be the square root of, if I use my calculator, I'll have, okay, so if I multiply this now, it gives me 4.9358 times 10 raised to the power 12. Okay, so that's when I multiply the numerator. So if I divide by 1.6, this will give me the square root of okay, so this will give me 3.085 times 10 raised to the power 12. Okay, 3.085 times 10 raised to the power 12, and if I find this, so the square root of this now will give me, it gives me 1756 416.81 meters, which is the standard form. R will be equals to 1.756 times 10 raised to the power, move 1, 2, 3, 4, 5, 6, and 10 raised to the power 6 meters. Okay, so that is the radius of the planet. The radius of the planet is 1.756 times 10 raised to the power 6 meters. Okay, so the next thing I'll do now is to find the diameter. The diameter of the planet now, diameter of the planet D is 2 times the radius. That D is equals to 2r. So it means that D equals to 2 times, and r here is 1.756 1.756. That's 1.756 times 10 raised to power 6 meters. Okay, so if I then multiply it, 2 times 1.756 exponent 6. Okay, and this will give me 3512,000 in meters. That's the diameter. So I can convert to standard form. Diameter D will be 3.512 times 10 raised to power 6 meters. Okay, that's 1, 2, 3, 4, 5, 6. Okay, that's the diameter. So I'll write it down there. Diameter is 3.15, so 512 times 10 raised to power 6 meters. Okay, 3.512 times 10 raised to power 6 meters, which is the diameter of the ball. Okay, so let's look for the escape velocity. The escape velocity now will be, okay, so let's find the escape velocity of planet C. Say the escape velocity VE is the square root of 2gr. Okay, so that is VE equals to square root of 2 times g. We obtain the value of g as so we had the value of small g as 1.6, and then the radius as we had the radius as 1.756 exponent 6. Okay, so that's my radius, 1.756 exponent 6. Okay, so if I multiply everything now, I'll be having my escape velocity as the square root of, okay, if I multiply this now, this will be 55619 200. So find the square root now. The square root of this now will give me square root of 5619200. 200. Okay, this will give me 2370.49 meters per second. Okay, which is anything as 2.37 times 10 raised to power 123 meters per second. That's the escape velocity. Alright, that's the escape velocity of the planet. So I'll write it down there. 2.37 times 10 raised to power 3 meters per second. Alright, so take note of this. We have solved them. We've got the value of the weight of 10 kg ball as this. Then we also got the value of the mass of planet B. Then we got the escape velocities as well. These are the escape velocities we saw for each of them. And then the diameter of planet C is this. We solved each of them. Alright, we are still on the concept of escape velocity, and the third question here tells us for a satellite which is close to the Earth's surface, its radius of orbit may be assumed to be equal to the Earth's radius, and R is 6.4 times 10 raised to power 6 meter. Estimate, Roman figure 1, the speed of the satellite. Roman figure 2, the period of rotation of the satellite. Okay, so quickly let's look at that. So the first one there is the speed of the satellite. Okay, so how do we find this now? Now what we'll do is to equate Newton's law of universal gravitation, equating it to centripetal force. Okay, so we said recall that F is G MEM over R square. If you call this one also F is mv square over R. Call this 2. Okay, this one is the force of the magnitude of the gravitational force gotten from Newton's law of universal gravitation and this one is the centripetal force. Centripetal force is mass times velocity raised to power 2 divided by the radius. Okay, so if I equate, I say equate equation 1 to equation 2. So if I equate the both of them now, I'll be having G MEM over R square is equals to MV square over R. Alright, so the mass, we cancel out mass, and the radius, we will reduce one of these. So I'll be having G ME over R equals to V raised to power 2. Okay, that is this. Okay, so remember that this mass, we cancel out mass, and this we reduce one of these. So I'm left with GME over R equals to V square. Alright, so if I then take square root of both sides, I'm having GME over R raised to the power of half is equals to R square or raised to the power of half. This will eliminate this, and the radius there is the square root of GME over R. Okay, and then that's my velocity. Rather, my velocity is this. So the velocity of the satellite is this. Okay, velocity of the satellite is this. Alright, so I'll come back again. We are given the radius of the earth as 6.4 times 10 raised to the power 6. Then we'll look for the mass of the earth. Okay, look for the value of mass. Okay, so you can call this velocity of the satellite. Velocity of the satellite is Vs. Okay, you can call this equation 3. Okay, also recall that G is GME over R square. Okay, so if I make M subject to formula now, I'll be having that G R square will be equals to GME divided by the coefficient of ME. ME will be equals to G R square divided by capital G. Right? So if I put it there, if I substitute it there into this equation, if I say substitute value of ME into equation 3. Equation 3 now will change. Now I'll have velocity of the satellite. I'll be having velocity of the satellite as this is square root of G times, now in place of the mass of the earth, I will substitute G R square over capital G, that is G R square over capital G divided by the radius small r. So capital G will eliminate this, and finally I'll be having this velocity of the satellite as the square root. That's velocity of the satellite as square root of small g r square over small r. Okay, and that will give. Okay, so you see that r now, you cancel out one of these. So my velocity of the satellite now becomes the root of gr. Okay. Alright, so by substitution now, Vs is equals to square root. Acceleration to gravity on the Earth's surface is 9.8 meters per second square, and radius of the Earth is 6.4 times 10 raised to power 6 times 10 raised to power 6 meter. Okay, so it means that Vs will be square root of 62,720 000. Alright, so if I find the square root now, velocity of the satellite now will be the square root of this gives me. Okay, so the square root of this now is 7919.59 meters per second. Right, this is the velocity of the satellite. Okay, that's the speed. The speed of the satellite is 7909.59 meters per second. Okay, now the next thing that we are told to find is the period of rotation of the satellite. Now we know that period of rotation or period of oscillation, it says the period period of rotation of satellites. Okay, so from our knowledge of simple harmonic motion, okay, so this is it, period of rotation of satellites. The angular velocity omega is 2 pi f, and the frequency is 1 over t, isn't it? Okay, so it means that if I put this into this formula now, I place it into this formula, I'll be having that omega is equals to 2 pi multiplied by 1 over t. So omega will be 2 pi over t. Okay, so make t subject of formula. If I interchange position now, by interchanging positions, I have that t is equals to 2 pi divided by omega. Okay, so take note, omega is 2 pi f, and frequency f is 1 over t. Alright, so what we are looking for is the period of rotation. Now the formula for period of rotation is this. We got this from simple harmonic motion. The angular velocity is 2 pi f. F is the frequency, and frequency is the reciprocal of a period. Okay, so if I place it into this equation, in place of f, I write 1 over t. So 2 pi times 1 is 2 pi divided by t. If I interchange positions, t will come here and omega comes here. That means omega, t is equals to 2 pi divided by omega. Omega is the angular velocity. So substitute the values now. Have okay, but also recall that linear velocity is angular velocity times radius. Linear velocity is angular velocity times radius. So angular velocity omega, angular velocity is v over r. Okay, angular velocity will be v over r, which is linear velocity divided by, and we had the linear velocity as 7919.59 divided by my radius. The radius there is that is 6.4 times 10 raised to power 6. So if I divide this now, omega will be equal to that will be this week. This is 1.24 times 10 raised to power minus 3 radians per second. Okay, that's when I divide that. When I divide that, it gives me 7. This divided by this gives me 1.24 times 10 raised to power minus 3. Okay, so I will then place it into the formula. The formula there is t equals to 2 pi over omega. So it means that, say, therefore t is equals to 2 pi omega will be 2 times 3.142 divided by omega is 1.24 times 10 raised to power minus 3. Okay, so angular velocity now will be 2 times 3.142 give, this is 6.284 divided by 1.24 times 10 raised to power minus 3, and then I'll be having t. If I divide it now, I'll be having 5067.74 seconds. Okay, 5067.74 seconds. All right. Okay, so that is it. We first got the angular velocity as 1.24 times 10 raised to power minus 3 radians per second. Then we are able to get the period using that, put the value of angular velocity there. Then you have finally 5067.74 seconds. Alright, and then we also solved and got the velocity of satellites as this using the formula root GR. Alright, thank you.